An apple may be labeled as having 95 calories, but open a chemistry textbook and it will tell you that it takes thousands of calories just to heat a single cup of water. To find out how much energy is actually in food, scientists measure its gross energy by burning it. They use a bomb calorimeter. A dried food sample is burned inside a metallic chamber, and a thermometer measures the total heat released into the surrounding area during complete combustion. In physics and chemistry, the small calorie, written with a lowercase c, is a very strict baseline. It is defined as the exact amount of heat required to warm 1 gram of water by 1 degree Celsius. On a nutrition label, that capital C acts as a hidden multiplier. 1 food calorie is actually 1 kilocalorie, equal to 1,000 small chemistry calories. To connect back to standard units, 1 food calorie is exactly 4.184 kilojoules. Scientific words carry traces of how they are measured. Missing a single capital letter means miscalculating human energy by a factor of 1,000. Your body is not a literal furnace. You don't extract every single joule of gross combustion heat from the food you eat. Instead, we have to estimate metabolizable energy, the energy actually available to your body after digestion and metabolic losses. This formula shows how we estimate that energy using the Atwater factors, commonly called the 4-9-4 rule. We get an average of 4 calories per gram of carbohydrates, 4 per gram of protein, and 9 per gram of fat. Let's run a baseline problem. Suppose a food item contains 24 grams of carbohydrates, 6 grams of protein, and 8 grams of fat. We plug those inputs directly into the equation. Multiplying out those factors gives us 96 calories from carbs, 24 from protein, and 72 from fat. Adding those together produces an exact mathematical total of 192 calories. But if you pick up the physical package for this exact food item, the label says 190 calories. The math isn't broken, and the label isn't necessarily a misprint. The Atwater factors are averages. Food labeling is subject to specific rounding rules, laboratory analyses, and natural variation in the ingredients themselves. Food labels represent practical approximations, not perfect exactitudes. This label highlights the most common trap in nutritional mathematics, the serving size multiplier. Every quantity on a nutrition facts label refers only to the stated serving. If our previous 190-calorie package actually contains 2.5 servings, we have to multiply to find the true whole package energy. 190 times 2.5 equals 475 total calories. Now test yourself. Here are new inputs from a label: 18 grams of carbohydrates, 5 grams of protein, 7 grams of fat, and 2 servings per container. Pause the video and calculate both the estimated calories per serving and the total package calories. First, we estimate the serving energy using the 4-9-4 rule. 4 times 18 plus 4 times 5 plus 9 times 7 gives us an estimate of 155 calories per serving. The actual printed label might round that 155 estimate to 160 calories. To find the final whole package energy, we apply the multiplier. 160 calories multiplied by the 2 servings in the container equals 320 total package calories. Accurate nutritional literacy relies on 2 distinct skills: the chemical estimation of the macronutrient formula and the proportional reasoning of the serving multiplier. Now we apply this math to the energy expended by the body. A common research claim states that quiet standing expends roughly 0.15 calories per minute more than sitting. This dimensional analysis equation maps out a 6-hour shift. 0.15 calories per minute multiplied by 60 minutes in an hour multiplied by 6 hours equals 54 extra calories expended. We have to challenge the resulting number. The human body is not a simple combustion engine, and it does not draw power at a constant rate like a 100-watt light bulb. That 54-calorie result is highly subjective. It relies on hidden variables that vary wildly between individuals, including metabolic differences, the constant regulation of body temperature, and the baseline energy required for organ function. To read nutritional claims accurately, keep this summary in mind. First, units matter. 1 food calorie equals 4.184 kilojoules. Second, use the 4-9-4 rule to estimate metabolizable energy. Third, always check the serving size multiplier. And fourth, recognize that biological systems are not rigid machines. The mathematics of multiplication is perfectly exact, but if a calculation fails to identify the biological assumptions beneath the numbers, the math will only produce an overconfident, inaccurate claim.